This course is finished by a laboratory exercise, and you are supposed to go through this exercise and to write a protocol in the same way as you do in real laboratories. I will explain you now the key points of this exercise. The idea is to verify the Clausius-Clapeyron equation by simulations, and we will use a two-dimensional model of matter. The software used is simenw1, you already know it, and the model that is inside is a 8-4 type potential. You know that Lennard-Jones is 12-6. Here we use 8-4 because we are in 2 dimensions. And this potential is truncated at 4 in certain dimensionless units. And it is also smooth so that it can be used in molecular dynamics. In addition to this model, we have walls. The walls are composed of the same type of atoms but smoothed in the wall that is integrated over the wall. If we do this, we'll get this potential. The attractive part contains this negative term. Negative means attractive, and the repulsive wall doesn't contain this attractive part. The code is written in certain dimensionless units so that we will keep the Boltzmann constant as unity. It means that energy and temperature are measured in the same unit, in fact dimensionless units given by this potential. And all quantities will be given per one atom, not per mole, as is usual in chemistry. So the task can be summarized as here. We create a system which contains 2 phases, like here. That is with an attractive wall, a repulsive wall. Here there is liquid and there is a vapor here. And the system is periodic in the x direction. This allows us to determine the vapor pressure of gas in equilibrium with this liquid. We will do it in 2 points for 2 temperatures, and from this we can calculate the vaporization enthalpy from the Clausius-Clapeyron equation. In 2 dimensions we will need some corrections, okay, but it's doable. But in simulations we can determine the vaporization enthalpy directly, because we know all energies, all quantities. To do this we will use the NPT simulations of 2 systems, liquid and vapor at the same pressure and temperature. And we will compare both methods. When simenw1 creates a configuration, it starts from a random distribution of particles. Then Monte Carlo simulation is run for some time to remove overlaps, and then we can start with molecular dynamics. This is done automatically. Of course, we can switch the method too. For the equilibrium calculation, that is equilibrium liquid gas, we use molecular dynamics. It is based on the leapfrog algorithm and the Brenten thermostat. There are other possibilities. For calculating enthalpies of both gas and liquid, we will use Monte Carlo, NPT Monte Carlo, that is at constant temperature and pressure. In the equilibrium calculations, we use pressure, which is defined simply by the average force acting on the top wall, and is divided by the edge length. Note that we have a 2-dimensional system, so that instead of area here we have the edge length, and this is the pressure. We can use also the real force. For the equilibrium, only one component of the pressure tensor, and for NPT simulations we need to know the pressure too, and we use the virial of force method to calculate pressure in simulations. You know from lectures on physical chemistry the Clausius-Clapeyron equation. This is the integrated form, and to derive this we needed several simplifications of the original equation, of the original Clapeyron equation. First, the vaporization enthalpy here is in molar units, that's why we have this gas constant here. This vaporization enthalpy doesn't depend on temperature. We also assume that the volume of liquid is much less than the volume of vapor. And we also assumed that the gas, the vapor, is idle gas. But we have a two-dimensional system. Some things are a bit different than in 3D, and particularly this red assumption of ideality of gas is quite inaccurate. These two are valid up to, let us say, 2%. We are not going to be so precise, but this should be fixed. Okay, there are several methods how to fix this. Some of them would be quite difficult and precise, like to integrate over the whole temperature range, but I chose one compromise, simple method that will cover most of this error. I will assume that the compressibility factor of gas at the saturated vapor pressure doesn't depend on temperature. Certainly it does, but if we calculate it at the center in between both states that we will consider here, we will get a correction that isn't so bad. With this correction, the corrected Clausius-Clapeyron equation is here. Here I assumed that the Boltzmann constant is unity. We use dimensionless unit, and instead of molar quantities I used the quantity per one atom. Otherwise the equation is the same. And we will run a simulation at this average temperature. We can calculate the vaporization enthalpy from enthalpies of both liquid and gas. To do this, we will run two NPT simulations. We will run NPT Monte Carlo simulations. The enthalpy for either simulation is a sum of three terms. This is the average potential energy, the average kinetic energy, and pressure times the average volume. In the NPT simulation, pressure is constant and volume fluctuates, so that we need the average volume here. And the vaporization enthalpy, if it's per one atom, is just the difference of both enthalpies. In Monte Carlo, temperature is a parameter of the simulation, and the kinetic energy is calculated, and it is the same for both phases, because these phases are at the same temperature. So this term actually cancels out in this difference. Usually, if we simulate compounds like water and so on in 3 dimensions, the situation is a bit simpler. We assume that the density of liquid is much larger than the density of gas. It is the same as here, and for water at normal pressures it really is valid. It is the difference of 4 magnitudes. Then we usually assume that vapor is either gas, and if we have a rigid model of water, it doesn't have any internal degrees of freedom. It means that the potential energy in the gas phase, that is this term, is 0. With certain approximations, this can be used for molecules that do have some degrees of freedom, but these degrees of freedom are not too much affected by the liquid environment in liquid, so that then both terms cancel out. Both internal potential terms cancel out. Only internal ones, the external, of course, in liquid are something negative. I already said that these kinetic terms are the same, and if we put all this together, we'll get this simplified formula for the vaporization enthalpy. In this case, it's minus the average potential energy in the liquid phase, normalized, plus this term which comes from PV using the ideal gas equation of state. Here we will not use this because we know our vapor is not ideal. You have already installed simulant. If not, just follow these rules. This is the web page, or you can use Google to find it, download and unpack to a directory. A few notes that may be useful. You will calculate certain data and they will be exported to a file with this name. As a default, a decimal point is used. You can change if you wish, for example, to use a Czech version of Excel. You can change this to a comma in panel measure. Also, you can change its name if you wish. The rest of this presentation consists of steps that you are supposed to do. Probably it's not too much for me to show you. I will just show the very beginning of this. So we have simulant running here. There are already 300 particles. You can change this if you wish by a slider. You can see that molecular dynamics doesn't survive this. If the simulation is very slow, you can go to a lower value here, but well, 150 is the absolute minimum. Then in the prepare system menu, you will get vapor liquid equilibrium. For the calculations to be done properly, choose here show quantities. Here you will see the quantities calculated on the fly, and this will cause that the frames will be shown every 15th molecular dynamic steps, so this looks faster, and also it will converge faster. And we can also change the measurement block up to 100. The individual points will appear a bit slower, but they will appear, I hope. So that's the first slide. In the second slide you will start with determining the first temperature. So you can either write it to that command field, and it's in the format variable equals and the value, that is for example 0.55. You can see that the temperature changed here. We can also use this slider. For measurements you will just click record, but before doing this, watch whether the configuration looks equilibrated. So this is recording. You will see here numbers which correspond to the blocks that are calculated. If you accumulate 100 blocks, that's okay, and you will stop this. This is not 100 yet, but I'm not going to wait. And these quantities will be written to a file, and you will find it in this file and can analyze later. You will repeat the simulation for the vapor liquid equilibrium at a different temperature, let us say 0.7. You have a range here, it doesn't have to be exactly this, and simulate again. And after you have two data points for this vapor-liquid equilibrium, that is two temperatures and two pressures. You will find in the table pressure on the top wall. You will calculate the average temperature and average pressure. Remember that the average pressure should be calculated as this geometrical mean, because it depends on temperature, or better on inverse temperature as an exponential. So this is perhaps a point to note. And with these temperatures and pressures, you will run another simulation. It may happen that the kinetic temperature that you find in this file will differ a bit from the temperature you set. Then it's better to use the temperature that you find here. It's not a big difference, but it's a bit better. Then you will run an NPT simulation. There are several steps because we cannot easily switch just to NPT, so we first must prepare the system that is either gas or later a liquid. We start with gas. So to do this, we must first set the density to a very low value, so that we simulate gas and there are no droplets there. Then we switch to NPT using the method, and any even tiny droplets would disappear, so we are simulating gas. After several steps and several blocks calculated, we save again using a record and find the data in this file. Now we have both pressures and also the average compressibility factor, and calculate the vaporization enthalpy, and also the estimated uncertainty. It's approximated because the accuracy of the compressibility factor is quite good, so that essentially these inaccuracies in the pressures are leading. Note that here we are using the relative uncertainty standard deviation because we have logarithm here. Then we will calculate at the same average temperature and pressure the liquid, so the simulation will be at the same conditions, only we must prepare liquid. To do this, we switch back to NVT. Also, we set automatically the Monte Carlo move. It's important because the productive run then must be written back to constant Monte Carlo move, but with the Monte Carlo move good enough for gas, we wouldn't calculate liquid. It would be very inappropriate and very inaccurate. Then we will create a dense system by changing density by a slider and return back to NPT. Wait a minute until it is equilibrated and to measure again. In the file we will find the enthalpy of the liquid and calculate the vaporization enthalpy. And the last task is to answer these questions. That is, at this moment you should have two values of the vaporization enthalpy obtained by two methods. So your task will be to compare them and to verify whether they agree at the 95% confidence level. To calculate this, you are supposed to calculate the difference of both values, so that we compare the difference to 0. Then to calculate the standard error of this difference, it is one standard deviation, and then to determine the 95% confidence limit, it's twice the standard deviation range. And you should answer the question which method is more accurate, which method is subject to systematic errors, and also how it works in a real experiment, because in a real experiment the answer is the opposite. So the last question for you is, which method do you know which uses in a real laboratory experiment to determine the vaporization enthalpy? Thank you for your attention.